This blog is about how we can train more efficiently mixture of experts models at scale with different PyTorch tools. So, in order to understand what a mixture of expert architecture look like, let's first kind of understand what a transformer architecture looks like, because we are building on this. So, a transformer architecture, if you think of it in the bigger picture, has an embedding layer, then multiple transformer blocks stacked to each other, on top of each other. But if you deep dive into the transformer block, you have the attention block and then the feedforward network. Then in the feedforward network, you mainly have a fully connected layer and softmax that creates the final probabilities for the next token. And this is the output of a transformer block. Now, in the mixture of experts, we focus and we replace this block with a mixture of experts block. And what happens here is that the gating network takes its token and produces a set of weights that determine which expert we will route it to. So during training, we pass new tokens and we update and tune this expert. And in this way, we enable the network to specialize and learn the difference between these
Just
experts.
to clarify,
Now,
you're routing tokens to the various experts. Okay.
Yes, we're writing tokens to experts. So each expert will take different set of tokens, think of it, that specializes in different things, right? They are experts on something, let's say. And then all of these tokens are passed to the expert weighting layer, where they are actually reweighted to push to the final to push out to create the final output for the mixture of experts layer. Now, if you're asking why did we even create this architecture and why should you care about it, is that in general, given your budget, it creates a more efficient training. What this means is that because the gating network only sends tokens to a subset of experts, this means that some of the experts are not being used or tuned during the training, reducing the computational load. So this means that as a result, the capacity of the model, so the total number of parameters can still be big, but without increasing the computation we need to train this model. So while we can have a big model, we don't need to use all the parameters at each point in time during the training process. And during inference, when you get the request, only some of these experts will be kind of triggered or used to create the request, making, again, less computationally expensive, or it's a more effective architecture in terms of inference, because you have a lot of parameters, but only some are triggered to create the final response. However, you need to keep in mind that even though we use some of the experts while inference, all the model needs to be loaded in memory. So again, if you have a huge model with a lot of parameters, you have to account for this. So it's not that you can put in memory only some of these experts. You load all the model, but just some parts of the architecture are being triggered to create the inference. Now, a question that comes up is how many experts and how do you define that? So, like, a rule here is that the higher number of experts we have allows for a larger model to allow the model to be larger and learn more without increasing the computational cost. So the model has capacity to learn, but again, after a point, how many experts can you have? So after a point, you see the performance actually decreasing. And the number of experts can be chosen again by thinking in mind what I'm planning to inference. Like if you have a lot of mixture of experts, you'll have to have a bigger model, more parameters, so heavier model to serve at the end. So keep that in mind. Another thing that also it's interesting is the top K. So what is the top K? So as we said here in the gating network, we first need to predict the probability value for each expert, and then we route the token to this expert, actually to the top K experts. So the token will be routed to the top K, top 1, 2, 3 experts that we have the higher probability for. So the more experts, right? So the lower the K while training, this means that we have smaller matrix multiplications to do, allowing for free computation, which is not that which is not that effective. However, during inference, a higher top K kind of may slow down the inference part. So the more top Ks we have to produce and pass the tokens to calculate the final response, bigger matrix multiplication we have to do, so the slower will be our inference. Now, mega blocks, which is we hear a lot about mega blocks lately.
What is
What is
megablocks?
it? What is mega blocks? It is an efficient mixture of expert implementation focusing on this sparse matrix multiplication. So, in order to understand what this does, let's understand what was happening before mega blocks. So before that, what we had to do is to, given that its mixture of expert takes different numbers of tokens, right? As we said, this is based on probabilities, again, which token is going to go to which mixture of expert. So this means that some of them had to take more, some of them had to take less. So me as a user before the mega blocks, I had no way to control it, and I had either to drop tokens from the computation or waste some computation that other mixture of experts were not doing a lot of work. Very simplistically. Now, with this library, what we can do is we can do uneven token assignment and allow full GPU computation and utilization while we have this uneven token assignment. So its expert can receive a variable number of tokens, and the expert computation can be efficiently performed using this sparse matrix multiplication. So we allow this diversity in the number of tokens by still allowing the full utilization of the GPUs.
Makes sense.
Another thing that is actually being used for the mixture of expert architecture is the expert parallelism. So when we're talking about GPUs usually are optimized for large-scale parallel computations. So the larger the operation we have, so the better we can utilize these machines. So we can have much better efficiency utilization of these GPUs. Now, how can we achieve that? How can we push the barriers and make sure that we fully utilize the GPUs? We can place these experts into different GPUs. So for each GPU, we place expert 1, and a different GPU, we place expert 2. Instead of just setting the weights, as before, we were used to share the weights to any GPU we had in the cluster. Now we focus each expert into a specific GPU, and we don't move weights, but we move the data. So what happens now is by moving this data instead of the weights, we can aggregate data across multiple machines for a single expert. And in this way, we can do much larger matrix multiplications that we said before, fully utilizes the GPUs and pushes the boundaries to the GPUs. So what we need to do here is bigger matrix multiplications to make the best use out of the GPUs that are amazing for this purpose. And we do that by, instead of replicating the weights across the GPUs, forcing specific experts to specific GPUs and pushing the data to the specific GPU that the expert needs to specialize on.
Got it. So the data moves instead of weights. Okay.
Yes. Now, the last thing is we have done another post around another video on this, but it's around FSDP, as we call it, or fully sharded data parallel, and hybrid sharded data parallel. So 03, as you can see here, is a form of data parallelism, and it's a fully sharded data parallelism that what it does is the weights and the optimizer are sharded across the GPU. They are not replicated, like copied, they are sharded. So parts of the weights and parts of the optimizer are sitting in different GPUs, and each GPU only stores a subset of the full model so that we really reduce the memory that we take from each GPU to store this kind of data and metadata. And as we scale to many GPUs, we have the problem of communicating between the GPUs and sharing metadata and data to the GPUs. So apart from the fully shared data parallel, you will see that the hybrid sharded data parallel is also being used, which what it does is it shards the model and the optimizer across a specific subset of GPUs, and then it replicates this multiple times to fully utilize the GPU. So it replicates it to a specific GPU, shards to a specific GPU, and then replicates it till it fully utilizes the GPU. So you'll see a combination of fully sharded data parallel and a hybrid sharded data parallel being applied on this, again, through PyTorch libraries. The last thing is around checkpointing, which is interesting because, as you train these big models, then you have to checkpoint and keep track of what's happening during training. And these checkpoints actually are huge. So how do we communicate and manage this is interesting. So we have to checkpoint the state of the model. This we cannot avoid, which includes the parameters, the optimizers, and any metadata that is necessary so that we can restart the training in case there is a problem. But when a failure occurs, the system should be able to restart from the last saved state. So for this, we will use the PyTorch distributed checkpointing, which what it does is support some elastic checkpointing, which allows you to resume the training after the last checkpoint, but also it allows for sharded checkpoints. So each GPU will be able to save and load only the proportion of the model and the metadata that was responsible for, so that then it can just, instead of loading all the model and all the metadata unnecessarily, it only loads the model and the metadata that is required to continue the training that it was responsible for.